We're happy to have Ahsan to give us a talk on the algebra of the infrared with the twisted mass.
Okay. Yep. Thanks a lot for inviting me to speak on this topic. It's my first time at Berkeley, actually. So my talk is going to be about algebra of the infrared, which is a topic that has a reputation for being difficult, mainly because this 2015 paper, I think, at some point was the longest paper in Hep theory. But part of my talk, I hope, is going to be able to convince you that it's really not that bad. For the mathematicians, Kapranoff, Kontsevich, and Soyleman gave a very nice reinterpretation of this work in terms of secondary polytopes. And their paper, you will note, came before, but that was just because these people took their time to finish their paper. And then for the part about twisted masses, some of that, a much confused discussion, appeared in my PhD thesis, where some elements were there, other elements weren't. But today I hope to give a more complete version of the things that I was confused about in my thesis. And so, yeah, this is stuff that's upcoming with Greg Moore. Hope to finish it in the coming weeks. So let's see. So these are the basic references. So I'm going to start with just reviewing the basic web-based formalism. In other words, I'm going to be reviewing parts of this paper, and I'll do that because this isn't a well-known topic. So after some review, and then I'll once I finish up the minimal amount of things I'll need, I'll try to discuss the generalization. Okay, so part one is just webs. Let me just use my notes to make sure I'm not missing anything. Okay, so the basic philosophy of this, as the title suggests, the algebra of the infrared, is that, so I'm going to say some general words about QFT. If I have some type of 2D cohomological field theory, in other words, it's cohomologically topological field theory. In other words, it's topologically trivial. It has a topological symmetry, but there's a BRSC operator that implements that symmetry. So such a thing has an E2 algebra of observables. And in the presence of boundaries, it also has an E1 category or A infinity category of boundary conditions. Now, so the basic philosophy, so these are things you can argue to exist on general grounds. So the philosophy is that, so for 2D, n equals 2, 2, massive QFTs, these factorization algebras, should be computable from some basic infrared data. So,
what is the relation between 2D n equals 2, 2 massive QFT and some homological?
Yeah, the relation is that so I can take such a QFT and make it cohomologically topological by twisting, by procedure of twisting.
So the word these means factorization algebra is associated with topology.
To topological twist. Yeah. Mm-hmm.
And the infrared data, is that infrared, how to say, like, do you first take topological twist and then go to the infrared, or go to the infrared and not topologically twist? Or?
No, yeah. This sentence stands on its own. So you have a massive QFT, and then it has some infrared data.
The infrared data has nothing to do with topologically twisting.
But then using that infrared data, you can build the.
I don't know anything about infrared data. So the infrared data is a thing which is associated with QFT, but has nothing to do with topology.
So this data, so this data will exist just in this ordinary QFT, but it still is dictated by. So the list of infrared data is kind of biased by the kind of twist I'm going to be doing. So in other words, the data will be certain supersymmetry preserving data, not just So yeah, it's a certain biased list of things, but those things exist independent of the twist. I will be more clear about what I mean by that. So in other words, so my first aim is to tell you more precisely what I mean by infrared data of a QFT. So roughly speaking, these are things that are visible long distances. So infrared data here, so I can give a mathematical definition, consists of such a QFT consists of, well, so there's going to be 4 pieces to it. This is a finite set of vacua. So then there will be, so there's this finite set, then there will be an assignment such that the zi's are in general, so the set zi is in general position. So this is some one-to-one map such that the zi's in the complex plane are assumed to be in general position. So you have this finite set and a complex number for each of the elements in the finite set. And then you have a collection of vector spaces.
What does general position mean? No 3 in a line?
No 3 in a line for now. I mean, it has a more, there are some additional conditions, but I will suppress those in this talk.
5 and 5 are in a circle? Or
no. Yeah, that's okay. Yeah. Mm-hmm. So, and then for each distinct pair, ordered pair, ij, there is a z-graded vector space, Rij, such that Rij and Rji are closely related. There's some pairing. That's degree -1 and non-degenerate. And finally, there's a more subtle piece of data. So what is this? What are the pieces of data so far physically? This is just the actual vacuum of the theory. These are the vacuum weights, so that the zij's are the central charge in the ij sector. And this Rij is the space of Hilbert space, let's say, of ij VPS particles. And so, yeah, the 4th element is actually a little less familiar.
Is Rij a finite dimensional?
Rij, yeah, Rij is assumed to be finite dimensional. Finite dimensional vector space over the complex numbers that is actually Z graded, but in some applications it's graded by Z torser. In some, if you want to be more precise. And so let me now mention the fourth thing.
And this is not assigned to a, like, if I just handed you an n equals 2, you could produce for any of these things.
Yes.
Without any information on what topological equations they
Yes, yes, yes. But Rij's are spaces of BPS particles, and what I mean by BPS means that there are certain supercharges, and those supercharges are the ones you use to twist. Yeah. And now, okay, so now the fourth thing. So there's 1, 2, 3. So you have these things with these pairings. These pairings will be a little important later. So this is, the fourth thing is called roughly, these are some particles in your theory, and particles have some interaction vertices. And then interaction vertices, not just any interaction vertices, but they have to preserve some fraction of supersymmetry. So satisfying some equation, satisfying some conditions. But these are just words. I can be more precise.
But they're associated to what?
Yeah.
As in, you have one such thing for each function of what?
I'll tell you. Yeah. So yeah, that's roughly, more precisely. So yeah, it takes a couple of minutes to actually say more precisely what this fourth thing is. Oh, I forgot I have a second board. Okay. Sorry. Okay. Okay. So yeah. So remember that I have these zij's, these complex numbers. So these are all vacua. A sequence of vacua is called fan of vacua. So now the corresponding central charges have phases that are cyclically ordered. So the picture looks like this. So this would be something with 5 vacua, and these are the central charges. The condition is that they'll always appear so that the phases are organized in this way. So now, so each cyclic fan I can assign. So let's call this I. I can assign a space Ri just given by the tensor product, the cyclic tensor product. For each of these rays, I take the corresponding space of solitons, and that's the space I assign to this fan I. And so I take the sum of all these things. Form this space. And so then there's a theorem. RC carries the of an L infinity algebra. Theorem means theorem.
I mean, there's no hypothesis.
There is a hypothesis. There are plenty of hypotheses. What do you mean?
What are the hypotheses?
The hypothesis is you have a finite set and a collection of complex numbers in general position and a space for each distinct pair of vacua with that pairing. So then I can form this space given by.
You're going to tell us the structure constants are.
Yes. So more on that, more on the L infinity structure in a minute. But so okay, yeah, L infinity algebra, and so before.
The nature of my complaint is, I can prove it very quickly. All the structure constants.
I know, yes, non-trivial.
Yes.
I will, yes. So okay, there is, in other words, given these BPS solitons and these vacuum weights, there is an L infinity algebra, and I'll tell you the structure constants in a second. But then, so my goal is to tell you what the interior amplitude is. Morey-Cartan element. In RC. So an interior, interior amplitude beta is simply just defined to be a Morey-Cartan. So in other words, so if I give you a massive n equals 2, 2 quantum field theory, the vacua, the vacuum weights, the soliton spaces, and this interior amplitude, the solution to this L infinity Morey-Cartan equation is determined. So so now okay, so
you just said something out loud and I understand the definition.
Yes.
But then you said something about the definition.
I just said that so this is part of the infrared data. So
but you said something about if you had the actual field theory to give you this.
Yes. Mm-hmm.
And we give you just like one of them, not like the family of that.
Yeah, it would give you a particular Morey-Cartan element. Yes. So okay, so let me just say a little bit about this L infinity structure. So.
By the way, I mean, suppose I had n equals 2, 2, whatever period, given by some drawing.
Yes.
How would you tend to say that?
I will describe that in a moment for Landau-Ginzburg model. Yeah. So Vivek asked about the L infinity structure constants. So so I'm not going to give a full proof, but yeah, the maps lambda n. So what does it mean for L infinity algebra? You want to give things that are appropriately graded and antisymmetric, such that the L infinity associativity equations hold. So the fundamental definition here that allows you to prove this is that of a web. So what we're saying is that a web is a graph drawn on the plane R2.
Say a word about how to think about how infinity. I understand TGLA, like just number one, number two.
Yes.
What is the higher?
How to think about it, or you mean like, do you want me to define it, or
How to think about what the structure is doing?
what the higher structure is doing? Are you familiar with things like homotopy transfer? In other words, you know, the L infinity. So if I give you a DG Lie algebra and you take its cohomology, you won't get an equivalent. The cohomology Lie algebra will not be equivalent DG algebra. Instead, if you insist on something equivalent, you generate higher brackets. It's a similar sort of thing that necessitates things like A infinity or L infinity. So yeah, a similar theorem holds for L infinity algebras. So I mean.
So A infinity has to do with the way this thing is generated. We have the picture associated with it.
Yes.
Boundaries of modularity.
Yes.
This thing has the boundaries of modularity.
Yes, that's right. So here you can think of it. If you started thinking of the configuration space. So one remark is that A infinity only has to do with the special case when you have one-dimensional boundaries. L infinity is something that actually applies to all dimensions. So in other words, if you look at the configuration space of endpoints on Rd, and you want to sort of compactify, there is a compactification of that moduli space such that so the boundaries, so you would be led to the, if you think of the boundary structure of the configuration space, compactified configuration space of points on Rd, you would be led to things like the L infinity relations, analogous to, in an analogous way to the holomorphic, to these disks that you were talking about. Okay, so I was, yeah. One thing I should mention, you know, for d-dimensional T2FT. So I talked about d equals 2 before. You have some ED algebra.
But it's also true that L infinity has to do with one input, many output, many input, one output. Yes, input numbers are circles. The same way that A infinity has to do this.
So this is a closed string.
It's a closed string. It's a closed string thing. That's right. So yeah, we have this ED algebra of bulk observables, and so in particular, this structure has shifted L infinity maps. Yeah. In fact, you know, this RC thing with this L infinity structure is exactly going to compute for you the space of bulk observables for Landau-Ginzburg models.
But just on spheres.
Yeah. Mm-hmm. Yeah, exactly. Yeah, so it gives you things analogous to the quantum cohomology. So okay, so how do you actually say what the structure constants are? So you have to consider webs. So a web is a graph drawn on the plane with faces labeled by vacua. And edges satisfy the slope constraint. So what is the slope constraint? It's simply saying that if an edge separates I from j, then this edge must be parallel to the complex number Zij. Yeah.
So just to clarify the bracket, you're saying this like element algebra is just like the Lie bracket given by like the restriction algebra, which is what algebra levels.
Sorry, repeat that question.
Are you saying this element T, this the algebra bracket, is like this big form that just algebra structure or
So in this line, all I'm saying is an ED algebra is in particular an L infinity algebra.
Okay.
When I say RC carries the structure of an L infinity algebra, this thing is meant to be the E2 algebra, but I'm just telling you that the L infinity structure on it.
Okay, so it does also carry the E2 structure.
But I think so that's spelled out less clearly. I think so. The full E2 structure, I think, is not spelled out in the paper.
And this is local observables.
Huh? Yeah, this is meant to be local observables of this compatible with this twist of for these n equals 2 comma 2 QFT. Okay, so yeah. So you have this parallel to Zij condition. So you have some you have pictures that look like this. So when I draw a picture that looks like this, it just means I have let's say 4 vacua, and then this graph is consistent in the sense that all these edges are such that this is parallel to Zij, this is parallel to Zjl, this is parallel to Zkl, etc. Etc. So in other words, there's a finite number of things that I can draw. If you assume, let's say, the fans are at least trivalent, finite number of things I can draw as webs once you give me the vacuum weights. So once I know the Zij's, I can enumerate all possible things. Of course, there's a moduli space. I can stretch and shrink, etc. The lengths. So so a web carries an action of scaling and translations of the vertices. So now the point is a given web determines.
So in this picture, do you want your edges to be the faces to be labeled by the vacuum?
Yes. Mm-hmm. Yeah. So if W is a web, there's a web up to this action. There's a map given by. The vertices are the vertices. In other words, okay, so a vertex in particular should be a cyclic fan, just by the edge constraints. So vertices. So these are graphs where the vertices, a vertex determines a cyclic fan. Yeah. So a given web determines a linear map on this space, given by, so I assign the space here, and I assign the space here. There's an edge that connects these two vertices. So here I have JK, here I have RJK, here I have RKJ, and then there's a contraction between them. So apply contraction for the internal edge, and I'll get something that gives you a component associated to RIJLK. And their subdivisions, yeah. So a cyclic fan, is simply a convex polygon in the W plane with vertices being the vacuum weights. And this web is simply a subdivision of this.
Every web can be translated into
Yeah. Mm-hmm. Yes. So let me just draw that. In fact, so this is the fan. This is the fan outside, and then it's a subdivision. Here you would have something like this. here you have 4 vacua and a vacuum in the middle, and then you have this kind of subdivision. So now for each of this kind of web, there's a linear map. Is the linear map clear? It's just applying contraction for each internal edge. Contraction, I assume, exists. And so W is.
I'm not sure. Requires metric.
So I assume the Kij's, remember I have, so this was assumed to be given. So, yeah. You're said to be taught if modulo, so if its moduli space is rigid, if it's reduced moduli space, by reduced I mean the action, so MW mod this action. Is a point. So in other words, the only so you fix the position of this, so you mod out translations, and then the only sort of scale of the web is that you can rescale it. So for example, this is a non-taught web, but this is a taught web. So you can do the counting. You can count how many moduli there are for a given web, and you only want the taught ones. In other words, the ones that are rigid up to scalings and translations. So
what is the top? The web picture, the top web?
This one?
The right one?
Yeah, this one is a taught web. Yes.
Rigid.
Yes, up to, so if you fix a scale and translations, there's nothing else you can do. Yeah.
Why is the left one not taught?
This one, yeah, I can scale this and this independently. I can.
Once you shift it, oh, it's just the envelope.
Yeah. So these ones, yeah. Whereas, yeah, if I had just had this would be taught. So.
Why does the web allow to cross without making a vertex, or is there
Yeah, they won't cross.
a statement or a definition?
Well, let's see.
You said it's a plane on graph, right?
Yeah. So yeah, it's a graph drawn on the plane.
I easily imagine. I'm just asking, like, are you allowed the line to cross without any vertex?
So the fact that the statement when I say it's drawn on the plane, then it means that there's no crossings. Yeah. Yeah. Okay. So now I can finally say what lambda n is. Lambda n is simply T is taught web with n vertices. And so this is a map. And then, the claim is that they satisfy the L infinity relations. So the essential point in proving this is you study moduli spaces of webs that are not taught, but that are one-dimensional, whose reduced moduli spaces are one-dimensional. So study So for example, if I study this web, so this is a web whose reduced moduli space is one-dimensional. Now I study what happens at the boundaries. So at the boundaries, there are two kind of things that could happen. I could shrink this edge, or I could shrink this edge. So one of them would correspond to this kind of degeneration. But then you also have to remember how it degenerated. So there's one end, then the other end would just be doing the similar thing for the other edge, where you had this thing, and then you have remember how it degenerated. So the point is now, each of these represents a composition. Each of these gives you a taut web, and the fact that you're remembering how things degenerated gives you a composition, and the fact that it appears as the boundary of a one-dimensional moduli space would mean that, yeah, this composition sums to 0, because the oriented boundary of an oriented one-dimensional manifold that carries orientation 0. So it's the usual kind of Morse theoretic proof that leads to a proof of this relation. So that's a very quick sketch. So you have this L-infinity algebra. And are there any questions about the?
What does it mean to say the algebra moduli against
Yeah, so I'm just saying each end corresponds to a pair of webs in a natural way. One telling you how the degenerated web, and the other telling you a web that remembers how what you need to do in order to recover the original thing.
But this is just some relation on the structure.
Yes, yes, that's right. Yeah. Okay. So now, yeah. So I have just from kind of some very simple assumptions, I have this L-infinity structure, and then yeah, beta, interior amplitude beta, is given. So the final piece of infrared data is Moore-Ricard element in RC. So something that satisfies. Well, this is probably the first 10 pages of that paper, but well, yeah. So I mean, yeah. And then of course, yeah. So then okay. So this is just the infrared data. Now I'm gonna, I guess, sketch what all of this stuff is in Landau-Ginzburg models.
But there's no natural way to associate these solitons.
No weight.
Is there a natural way to associate these solitons with actual full string states of circles?
So yes, there is, but I mean, like that requires talking about the Landau-Ginzburg models. So you're kind of asking how I can think of an element in RC as some closed string, as a state on a circle. Yes.
I guess the element of your RC is close to enough.
So no, an element in RC is a state.
RC is what? RC is the direct sum of
so yeah, RC is given by summing over all cyclic fans. So pictures that look like this and then you assign the cyclic tensor product.
I think maybe you want to ask about lambda.
Yeah, I guess so.
So now, yeah, so the closed string amplitudes are, in fact, not just lambda. The closed string amplitudes are lambda, are the deformed version.
Oh, I see. So each one of these you can associate to a little circle.
Yes.
With stuff around.
Yes.
And then that's the closed number.
Yes.
Great.
Yes. So, but I want to say, so things, yeah.
Lambda is a closed string. Yeah, and RC labels what happens to that.
Yeah.
One third. An element of RC.
Mm-hmm. Yeah. But okay, so there's an important remark. This the L infinity structure given by taut webs is kind of the free. So there is a free L infinity structure given by taut webs. But then you have to remember that in a physical model there is a non-trivial Maury-Cartan element. So it's so then this is the one that's this is a new L infinity algebra given by
How do we define this?
So a Maury-Cartan element. No. So I didn't say anything about curved. I'm just saying that curved.
You need to ask me the following question.
Yeah.
Simply in the bond paper, if there's an abstract development problem that says if you begin with any what you get
2D.
whatever kind of theory, then out comes some element like this.
Yeah.
So Ian is asking you, what is the procedure by which you produce that element from it?
Yeah. I will explain that in a bit. But I mean, so I want to say that so there's an L infinity structure coming from just taut webs, but then given a Maury-Cartan element, I can deform the L infinity structure just by using this formula. These things will also satisfy the infinity equations, and so that's the L infinity structure that actually gives the closed string.
That formula says what? What's the meaning?
It means lambda n is given by summing over all the things in the free, summing over all.
Is that an identity or a definition?
It's a definition.
The guy on the left
It looks like you're writing that thing is equal to its first term.
Thanks. Yes. Lambda n of deformed lambda n of beta by definition is given by summing over the previous one with these insertions. So there's a web way of interpreting that, which is to calculate lambda n, I draw all webs with n plus k vertices, taut webs with n plus k vertices, but now I insert beta in the extra vertices.
Is there some statement that is it a true fact that any 2D equals to a deformation of some kind of free theory in some sense?
Well, so it's the only thing I can say is like usually there's kind of an analogy. So in quantum field theory, there's a free quantum field theory, and then there's an interacting quantum field theory. So it's in that spirit that you have this free L infinity algebra, and then you have this non-trivial interaction amplitudes, and that gives you the.
When you produce
Mm-hmm.
What is there a? If I begin with the same theory, if I produce a different theory, which I get the same element structure with beta equals 0.
That might not be a consistent theory. I don't know. I don't know. It's possible. It's possible. I mean,
That doesn't come with some procedure.
So, well, I mean, so beta is determined once I give you a Lagrangian description, like a Landau-Ginzburg one. No, that's not true.
So my question is it the view that if I begin with an n equals 2, 2 theory,
Yeah.
that I could deform it in its basic theory to some other n equals 2, 2 whatever theory, without changing any of the data until beta? So that this deformation takes place.
So I think,
It's like nothing to do with talk. I just sure.
yeah. So, yeah, I mean, I don't know if you can pick some random beta and say that, oh, that corresponds to physical n equals 2, 2 field theory. Yeah.
And the physical meaning of the Moore-Witten equation is that there has to be a beta that solves it. Is that?
The physical meaning of the Moore-Witten equation has to do with the fact that whatever interaction you turn on, whatever like your vertices are, have to be supersymmetric. But let me go to Landau-Ginzburg models because this is too abstract.
So it's a constant of supersymmetry, the Moore-Witten equation?
Essentially, yeah.
And remind us, beta is just
degree 2. Yeah, because this is a shifted L infinity structure. It's not really that relevant. Yeah, it's some degree 2 element. So, okay, going really slowly, but hopefully you guys are learning something. So Landau-Ginzburg models. Okay, so now remember I had V, I have vacuum weights, I have the RIJs, and I have beta. So in a Landau-Ginzburg model, we have X and W. X is some Kähler manifold, W is some holomorphic Morse superpotential. So V is going to be given by critical points. W. So this entire business involves fixing a phase, fix zeta. Phase. And Zi is just going to be given by the critical value times zeta inverse. So this is trivial. Rij is going to be given by the space of Ij. So it's, well, Ij BPS. Well, Ij gradient flow. Space generated by. So you look at solutions of, so letting phi a be a local coordinate on X. You look at solutions of this that asymptote to I at one end and J at the other end, and you assign a free generator to each such trajectory. It's actually best defined in terms of a Morse complex. There's a Morse function whose critical point equation is this equation, and you look at the critical points, which correspond to solids on trajectories, and you have a space like this. Okay, and because Rij is has a pairing with rji because you can take a soliton trajectory and reverse its direction. So you have these three pieces of data. Okay, the pairing part? Sure. So I'm just saying that if I have a solution of the soliton equation that goes from I to j, then I can produce, just by reversing x.
That's your definition.
Yeah, yeah, reverse the soliton. And finally, yeah, so beta, how is beta determined? Beta. So beta in general, what's the general form of beta? Well, it looks like, so suppose I have this thing and I have, some, let's say, basis of this thing. The general form of beta is that there's some number, well, not some, yeah, some number. I0, I1. N I0 times so this is a I0, IN, these are cyclic fans, and this is just the coefficient. Now, so the question is, how is this coefficient determined? So that is given by, and so what are these things? These things are in one-to-one correspondence with gradient trajectories, ij gradient trajectories. So this n of EA I0, I1 is given by, so what you have to do is you have to formulate a boundary value problem. So remember that these I1s, INs form a cyclic fan. So what you do is you put, so, and each of these carry soliton. What you have to do is you have to look at the solutions of the Witten equation. With these fan boundary conditions. And you look at the rigid ones. So this n is the oriented count of these things, of this moduli space of solutions with these fan boundary conditions. And that's n. So I can draw it a little bit more transparently in the dual polytope, dual polygon. So in the dual polygon, if I have some fan I0, I1, I2, 3, I4, then the point is I label each of these boundary components with a soliton trajectory, and then I want, so this is a map from R2 to X, and then under W, sorry, under C, I want this this thing to be filled in, and I want the boundary circle at infinity to trace out these paths, these particular paths. So you have this kind of fan boundary conditions. You count solutions of these things. So this is kind of complicated, which is one of the reasons why The paper is long, but you have this kind of counting problem that determines that tells you what beta is in a Landau-Ginzburg model. And the fact that this satisfies the Maury-Cartan equation, L infinity Maury-Cartan equation, has to do with the thinking about, well, what kind of if I have non-rigid moduli space, how can it degenerate? And it degenerates by things that look like webs. So that's a little dense. So please feel free to ask questions. So this is the discussion of Landau-Ginzburg models. Any questions about this? Yeah. Go ahead.
Maybe you'll say later, but like, so you're going to do non-linear algebra this thing. Do you know what like the linear algebra measure like a full one-by problem? Do you know what the full one-by problem is?
Well, it has to do with the fact that this is kind of meant to be an effective field theory of BPS particles, and effective field theories always, field theories in general, kind of in one-to-one correspondence with classical field theories, at least correspond to elliptic moduli problems. So that's the discussion relation between field. So I guess what you're asking, the way I'm interpreting your question is, the way I answer your question is, in general, there's kind of a relation between classical field theory and elliptic moduli problems, and that sort of thing is discussed in Kevin Costello's books. And this is just one sort of manifestation of that kind of thing. I don't know if that answers anything. Yeah.
So, another related course in mathematics, given such a thing, we consider Fukaya-Seidel category.
Yeah.
And it has some category, some category structure or whatever. So the L infinity structure you described here, what is its relation to that?
Yeah. So it's as proven in Kapranov's paper. So I will later describe. So just in a second, I'll describe the A infinity category in this setup. So that A infinity category has a Hochschild homology, which is this thing. So okay, so this is general Landau-Ginzburg. Now let me do a.
From that point of view, let me answer the next question.
Yeah.
Usually, the Hochschild homology, something like the Phi category, has to do with orbits and generally the orbit that fit the stuff. How do you see that in terms of this thing?
Yeah. So these cyclic fans of solitons correspond to a solution of the flow equation. Well, approximate solution of the flow equation where this is zeta wraps the circle.
This fact is playing as well.
Yeah. That's right. So
what's the meaning of the data that has it out?
yeah, I will explain. So now let me, okay. Oh shit. Okay, yes. Do I have till 4 or can I? Okay.
People will leave when they want to leave.
Okay. Because I'm going really slow.
I hope someone warned you. It's like the stupidest audience in the entire world.
I'm glad you guys are asking questions. Okay, I like the open-ended format. People can leave. Anyway, so let me even be more specific. So more specifically, quartate LG model. Sorry, I missed that. What did you say?
No, I thought zeta is fixed, right? Your z, so the rules of the game is that around
So,
soliton goes from one vacuum to
yes.
another, right? So zeta is fixed.
Zeta is fixed in the soliton equation, but not in the Witten equation. In the Witten equation, the zeta is the same zeta that appears in Zi.
But it's fixed.
It's a choice. It's a choice as long as it's.
Family of theory parameters, are you going?
Yeah. So in other words, this zeta has to do with the choice of supercharge I'm preserving. And yeah, so there's. I can let it vary if I want to. Yeah. That's right. So it's, this RC thing is, I guess, supposed to be 1/4 BPS local operators for a particular Q that depends on zeta. So in other words, this Witten equation preserves a particular supercharge.
So this is the place where it's different from the standard. Well, okay, you have some problems thinking about the open structure, but
Yeah.
in standard Fukaya-Seidel, zeta would be fixed.
So here it's also fixed. It's just, well, what do you mean by fixed? I'm making a choice.
Do I pick it once and for all?
I pick it once and for all. Yeah. So I mean, in this formalism involves a choice of zeta.
If that zeta varies around the circle.
So that's if I want to, if I want to give a interpretation of these cyclic fans in terms of closed string states, then their zeta wraps the circle, but then that also defines a system which preserves two supercharges. But let's not, we don't have to get into that particular interpretation. So now, so just to illustrate things a little more explicitly, let's say I have, this so I have X is C, and this particular superpotential, then let me just, so then, V is just I choose zeta to be minus I, which is something I do for convenience. So then vacuum weights are given by minus 3/4 I. I call this Z2 minus 3/4 4 pi I over 3. Call this Z1. And I have central charges that are looking like this. Central charges are just okay. So Z1, Zi is minus. So what are the? So this is the picture in the W plane, I guess. So these are the vacua. These are the weights. Now I have to say what R's are. So in this particular example, it's not hard to show that I have these critical points. One, which I label as and then it's not hard to show that there's a single gradient trajectory between each of them. So the particular R's now are all one-dimensional, and they have this funny fractional degree. The opposite ones are also one-dimensional, carry this funny fractional degree. That has to do with the fact that this usually in these solitons carry this charge fractionalization phenomena. And so now, and finally, I have to say what beta is, what the interior amplitude is. So there's a map from R2 to this target space C, such that this this particular thing is filled, and in the W plane, this particular thing is filled. So, and it's rigid. So beta is given by I12, corresponding to this cyclic fan. So this set of central charges allows for this cyclic fan. Just a second. Yep.
So this fact that kind of counting in Landau-Ginzburg, it basically makes some assertion that you can count this, which ought to be counted upstairs. In fact, we count it in the W plane. Is that the level of indices? Is that because the fact that the amount of homomorphicity of the function?
So I'm just saying my boundary value problem is such that this thing is filled up.
This example is only C, right? No, I'm not discussing example. So in general, the second way this works is when X is complex animal, holomorphic.
Yeah. Yeah. So yeah, this is the particular beta for the quartic LG model. So that's the vacuum data. So this is to illustrate, in certain concrete examples, this thing can be actually determined. Okay.
What's the vacuum to 2/3
Yeah, this is the so I'm just saying, so this soliton R13, R32, R21 has this degree that's 2/3. This is a kind of phenomena. You can ignore degrees if you like for this talk, because it's more detailed than I want to go into. But in general, these 2D solitons have this charge, this kind of charge. Log. That controls the sort of charge, the fractional fermion number. It has to do with the eta invariant of this soliton. Okay.
Are you going to solve the constraint vacuum for actual frame symbols? And constraint is closed frame problems or no frame problems?
Well, if you know,
there's a lot of questions about it, but they're basically.
Okay. The backside.
That's not giving enough information to the structure. It's a very close string information. It's going to tell us about open string.
Now let me talk about A infinity categories.
Eventually, you want to what is twisted?
Yeah.
What's the untwisted mass?
Untwisted, yeah. So untwisted mass just means W is a function.
Okay.
Twisted means dW is a closed one form, closed holomorphic one form. Yeah, with some non-trivial period. So, any other questions? So the construction of there's an L infinity algebra determined by this beta and these webs. There's a similar story for A infinity categories. So now I'm going to define a category with objects. So okay, I need to make some choices. So I choose H, half plane in R2, such that the vacuum weights Zij, such that boundary of H is not parallel to any Zij's. And then I will define a category, objects Ti, I and B, and the morphism spaces so how is RC defined? RC was defined by assigning a direct sum end to each closed cyclic fan. This thing is going to be defined by taking a sum end I equals I J for a half fan, and then Ri. So a half fan, more precisely, is just a set. A half fan of type Ij is a set of vacua, I1, In minus 1, J, such that the corresponding, so if this is my H, I'm choosing something, then the corresponding central charges are in this phase. Their phases are in this order. Okay, so that's a half fan, and then to a half fan I can assign the same kind of tensor product. So that's by definition the morphism space between from Tj to Ti. I write that as R hat Ij. So I sum over all these kind of fans that start at I and end at J, such that this stuff is in the half plane that I choose. And then I assign a space to each of these. And A infinity maps are now given by looking at taut half plane webs. So Mn is given by taut half plane webs with n boundary vertices, and it can have a number of bulk vertices, and beta occupies the bulk vertices. So, for example, this is a taut half plane web that would contribute to M2. Taut again means that so now these half plane webs carry an action of R plus semi-direct R instead of R2 because you break this symmetry. can only do translations along the boundary, etc. So yeah, they're rigid up to this group, and you insert beta into the bulk vertices, and that gives you a well-defined linear map from these morphism spaces to a target morphism space. So that's the rule for A infinity maps. Any questions? It was very quick, I guess. To define M2, sum over all such things with two vertices at the boundary, and in the bulk, for bulk vertices, you insert a beta.
And is there a differential? Is there F1?
Yeah, M1 would be things like this. A single boundary vertex, or even things like this. So in other words, beta with this kind of thing, or yeah, it could also be so single boundary vertex, and you have two bulk vertices, and insert.
But this never.
Yeah. So yeah, there is in general, of course, there's a differential, there's an M2, there's an M3, all higher brackets.
I understand what.
Yeah.
So for M1.
Yes.
M1, I'm supposed to have an input in.
Yes.
Yes. And output in the same
No, yeah. So.
Where do you specify the output?
Okay, so you have, yeah. So let's take this example. Or which example do you want to take?
Let's do the simplest thing.
Okay, let's do this thing. Okay. So now I want M1 from R hat IK to R hat IK, right? What's R hat IK? R hat IK is given by summing over all half-plane fans. There's this half-plane fan, and then there's this half-plane fan. So R hat IK is given by. There are other ones too, of course. Yeah.
But you don't allow bulk vertices there.
I do. This is a bulk vertex.
Sorry.
This is RIK plus.
So your definition of the hatted guy involves all the same thing.
The hatted guy involves summing over all half-plane fans. And if I have a web like this, which is consistent with having half-plane fans like this, then this thing would be something that maps this summand to that summand. By the fact that there's a beta. Beta lives in this thing. So you apply contraction and then you get that. So that's M1. Yeah, and similarly here, you have some fan, two betas, and then you get that.
And I want to think of it as.
Mm-hmm. Now.
So the differential is non-trivial only if beta is not zero. Is that correct?
Yep, that's right. Well, so this is important to remember that this is just the vacuum sort of thimble category. So yeah, and here it's true that in this thimble category, differential is only non-trivial if there's a beta. There's an important point, which is that there could be a bivalent beta, which just turns Rij into a chain complex. So if Rij is in general, we'll have a differential with Dij's. So of course there might be those as well. So I'm saying that there's one kind of bivalent fan that is there. And this is a plane fan, not a half plane fan. So it just means that.
You're saying that one of the summands was called Rij, that already came with the
I'm saying that, well, I'm saying that you can either think of R's as vector spaces, and this bivalent component of the beta equips these things with a chain complex structure.
I don't understand how is that something that was not contained in the discussion you just had, or
It was.
How is it contained?
Which discussion? Sorry. This.
The definition you wrote, does that already include whatever you're talking about?
Yeah, it does. Yeah, so.
And how does it?
It's just the fact that this is a bivalent fan, and interior amplitude has this component. Yeah. So Mina just asked if the differential. Mina asked about the differential, and I'm just saying that differential comes from beta, whether it's bivalent, trivalent, whatever.
Does it come from beta via only the discussion of half-plane bands?
Yes.
Or in terms of whatever you just wrote?
It comes only in the discussion of taut half-plane webs.
Okay. And so how does the thing you just wrote have anything to do with that discussion?
I think that was maybe an irrelevant remark that is just more confusing than illuminating. So we can just, not. Yeah. So this, in general, what I said here is true that, so, there's some infinity maps given by drawing half-plane fans, and the differential in particular, just look at taut half-plane webs with one boundary vertex.
And so these categories might have different stuff. So your Landau-Ginzburg model, any constraints on it, the target has to be just copies of C, or?
No, so I mean, it's not just, I don't even Landau-Ginzburg, anytime I have infrared data, there's an infinite. Anytime I have infrared data, V, Rij's, beta, there's an infinity
so
category.
So in such a theory, I could in general have different sets of symbols too?
And in general, there's a choice of H, and you can ask what happens if you change this half-plane fan.
What do you mean H?
H is some half-plane fan. H is some, half-plane as a subset of R2.
I think my understanding of what the big set was is that if you ignore what we discussed, began line with an algebra model, it's a certain thing you would do. And that thing involves having all of the curves somewhere. And what you might discover is that because W is holomorphic, so now counting holomorphic curves upstairs is the same as counting some diagrams in the image of W. You might discover that. Now, what is being told to you by this paper, as far as I understand, is that every n equals 2 to dimension 2 theory behaves as if it was a Landau-Ginzburg model for something in this point of view. But with another one Landau-Ginzburg model, it's still okay to write down what this is.
So for example, a B model has an interior amplitude. The B model has a collection of solitons and an interior amplitude.
Let me say completely different. If I hand you Landau-Ginzburg model, it might have some set of symbols. There is the associated A infinity category, A infinity amplitude that I might compute in any which way I want. Are you going to say that it's going to match this?
It's going to match. So in fact, the next, so let me just show you in some stupid in the stupid quartic LG model that things match.
Oh, well, actually, I thought that in the paper they said that there's a derived equivalent.
There's a derived equivalence, sure.
It's not the same statement as A infinity amplitude matches. In fact, it's very far.
Well, I mean, the
point is, I mean, what's defined here is, well, that's exactly a holomorphic curve count done with the equation. Counting some, let's say, whatever. Now, the usual subcategory is you count some other related but different decision zones, related but different. The way to interpolate from one to the other. And what that means is that you have a moduli space with boundary. On one side is this one, on the other side is this one. But what such a moduli space gives you in general is a derived equivalence. But I think the Fukaya category itself is only defined on the derived equivalence. Because the different choices you made in the defining the perturbation. So you have no right to ask for saying in the structure. We're going to have a given one on the infinity side.
Yeah.
No, because, sorry, there's the original Fukaya category before anybody derived anything.
No, that was never defined. There choices of perturbation data you use in defining the phi category
Well, it will be
will
something.
give you different things, but they're only A infinity plus S.
Yeah.
You never have to right.
Yeah. Yeah. So yeah, in general, the statement is okay. So I define the thimble category. I can take twisted complexes in this thimble category, and that is an A infinity category, which is A infinity equivalent to the Fukaya-Seidel category as defined by Seidel. So there's an A infinity equivalence between them. There's a physics argument for this in the paper, of the sort that you were talking. You know, there's some interpolation between the two. So, but anyway, so let me just show you in a dumb example that things agree. So for this Landau, and for this back to the quartic case, quartic LG model case.
My understanding is they're studying the same PDEs, but the difference is the set of the set of T, the set of range.
No. The P is different. This Witten equation is different than the.
Well, okay, in the usual category.
The brains are not different.
You will just forget about the perturbation that comes from doublets. But
basically the difference is in the Witten, so like in the usual Fukaya-Seidel you perturb at infinity the Lagrangians so that you count finite holomorphic curves.
But that perturbation comes from
the Witten equation do not perturb the Lagrangians. And you like let the holomorphic curve go to infinity, the equation is different, and you can interpolate between these two things.
Yes, and what interpolates between them, right? Is that instead of studying solution to the Witten equation, I'm going to perturb my Lagrangian at a flow that comes from the right hand side, which is a completely standard thing that you guys do all the time.
Okay, I'm glad you guys are learning a little bit. So yeah, stupid example. So remember that you had these central charges. So now let me say what r hat 1, 2 is. In this, these are arranged so that the only cyclic fan, the only half-plane fans are the ones with just one arrow. So this is just going to be given by C. This is just going to be given by. This is just going to be given by. And now there's going to be a non-trivial multiplication. So to define non-trivial multiplications, you have to look at taut half-plane webs with this particular configuration, and you can easily check that the only non-trivial web looks like this. And remember, there was an interior amplitude in this example that I wrote before, and this leaves the simple multiplication. So in other words, you get this kind of category, and this of course this matches what you would do in the Fukaya-Seidel category, where you would draw this you would draw this thimbles. So the thimbles, particular thimbles you would draw look like, I guess. And then wrong color. So then there's these intersection points and this holomorphic map. So there is this non-trivial multiplication given by this thing. So in fact, yeah. So these two things agree even in the even as thimble categories in this case. So you don't have to pass the twisted complexes for this particular example. So the message is that instead of looking at this triagram, it's reproduced by the bulk interior amplitude and this particular web combinatorics web diagram. So we led to the same thing. Okay.
Am I allowed to perturb it a little bit?
Sorry?
Am I allowed to perturb that picture a bit?
This?
No, perturb it symbol.
Yes, of course.
Isn't that triangle kind of flipped to something that's not homomorphic or just an orthogonal?
So I think you would. So here what you're doing is you have some you have these symbols, and then you're perturbing them a little bit, so you have this kind of thing. But yeah, I mean, the way to perturb things isn't unique, of course.
So if I tilt the right out a little bit, you'll have the same.
Yeah. So.
You didn't believe that, you wouldn't believe in the category at all. It is true, but if you didn't believe that,
Okay. Okay. So now.
I am confused about something.
Yeah.
Which is something which does not appear in the Fukaya-Seidel category. It's the business of describing a Hom between two things as a sum of all ways of factoring the Hom through other people.
Yes.
How does that appear in the picture?
Well, so in this particular example, it's irrelevant. Yeah.
How does it appear?
In general, it's important. So let's see. So okay, the way I guess you can see how it appears is so let's say you were doing things in this particular configuration and your thimbles were like this. Right? What GMW is doing is they're only looking at, RIJs are only looking at these particular things. So they're looking at this intersection, they're looking at this intersection, and they're looking at this intersection. To relate these intersections with what happens here, you have to do that kind of Picard-Lefschetz mutation, I guess. So in other words, this intersection is given is related to this intersection by a formula like so this is your one valent fan, and this is your bivalent fan. That's why they're in relation like this. Okay, so this was just a giant 1 hour 35-minute review of this paper. I did not talk about twisted masses, so that's going to be next.
Is this really well-defined as script, or do you have to classify the plane maybe to this, and put some stops on the boundary, and then?
You asked about his thing or Fukaya-Seidel?
Well, okay.
The question is basically like, where does it stop? The choice of the half.
I need to be careful about avoiding symbols.
No.
You would get the same, get something A infinity equivalent. For example, you could draw.
Your question is like, how do you wrap the symbols in infinity? And the answer is, would you do it down? So how do you draw it? The answer is, you go downstairs and
Downstairs being the W.
And you draw some straight lines here. And then if you're computing Homs in a certain order, you move them a certain way downstairs. And the only thing that's important is what kind of order you move them in. And then you just list them.
Yeah.
That's the share.
Okay. Twisted masses. So in general, the idea is that this vacuum data is just a certain set of nice assumptions that I'm making on the theory. But really the important thing is that the theory be massive. As long as I have a massive 2,2 theory, there should be some philosophy of like the algebra of the infrared, meaning that things that are visible in the IR should be able to reproduce things like A infinity category boundary conditions. So there's one particular example, so basic idea, philosophy of algebra of IR should hold in a more general setting. So in other words, you can go beyond. Should apply to more general QFTs. So there is a certain, so let me talk about that in a second. So more general n equals 2 QFTs than the sort considered. So there was some hypotheses indeed, but they were kind of weak, but they're still easy to violate. So the main hypothesis is that you have this kind of thing. So you have a finite set, and you have that the central charge, which in the previous case was just a definition, but the central charge is actually something that appears in the supersymmetry algebra, and you can compute that it's equal to this thing. So in particular, ZII is 0. Physically, this means that there are no II BPS particles. But in fact, it's quite easy to write down 2,2 quantum field theories where there are II BPS particles. And so they're massive and they have II BPS particles, but they don't have this kind of nice factorization. So the central charge in the IJ sector is not just a difference of two numbers. So for that kind of thing, you would need to generalize GMW. So anyway,
like for example, example has in mind when we're trying to do this kind of case in whatever, this kind of, there's some like infinite dimensional sense we view the turn silence functionals, infinite dimensional potential, complex turn silence functionals.
Well, yeah, so that would be an example, but that would be much like a fancy example.
Yeah, sure. But I mean, yeah. Whatever GMW do doesn't cover that example.
It won't, yeah, it won't. Yeah, because
this
yes, because this is the kind of assumption that's violated. So in your example, in this Chern-Simon example, ZII would actually be the action of an instanton. Yeah, if that makes sense. Yeah. So in general, ZII would be a charge K, where K is the charge of an instanton. But yeah, that's a much fancier example than what I'll need. So one simple way to go beyond this is, let's say you have some QFT with global symmetry with charge generator Q. So you have a U1 global symmetry with some charge generator Q. Then so in this supersymmetry algebra stuff, there's a construction known as the twisted mass construction. So I can turn on twisted mass for this U1 symmetry. and see how it affects the central charge in the sense that the central charge is a commutator of super currents. So then you would be led to something like a formula like this. So twisted mass corresponds to choosing complex number. So then you can indeed have you can have solid, well, you can have II BPS particles.
So when you say U1 symmetry, does this mean in particular thing comes from the symmetry of the target space?
In general, just means that a quantum field theory can have a global symmetry.
Not in general.
If
I wanted to get one from the symmetry of the target space.
Then you, for example, it could come from the symmetry of the target space, but then that's most directly discussed in the B model. In the B model.
Okay, but I don't want to discuss the B model.
In the A model, it would manifest in a slightly different way.
So it is not a symmetry of the target space of the A, that will not be wrong.
Yeah. So I mean, yeah, this twisted mass is kind of plays intricately with the kind of supersymmetry, like with the supercharge you want to twist. So by the way, the algebra of the infrared does apply to massive B models. It's not a big deal. So, okay. Anyway, so.
You're saying the kind of thing would be mirrored to a U1.
Yeah, exactly. So what does it mean? So this twisted mass construction is rather simple for Landau-Ginzburg models. So in Landau-Ginzburg models, we just assume that I have a target space X with a first homology that's, let's say, non-trivial, or the torsion part is non-trivial. So okay, B1X is not 0. And then, so what I can do is there's a well-defined, so the quantum supersymmetry algebra is there, only requires closed holomorphic one form alpha. And so then we'll say that this LG model has a non-trivial twisted mass. If there's a non-trivial period. So the central charge in a Landau-Ginzburg model is given by integrating the LG1 form over a path, and in particular, if there's a period, then ZII would be some path from the ith vacuum to the ith vacuum integrated, and this would be non-zero. Just a remark. So let me just make a.
I understand, but now I don't understand. The ZI.
So okay, what I'm saying is the following. So let gamma ij be the homology class of paths from the ith critical value to the jth critical value.
There's no such thing. There's many homology classes.
I said consider the set. So then there's a map from this to C, just given by integrating. So I can let.
So ZII is a set.
Yeah, ZII is a set. Yeah, ZII of gamma, I should say. Where gamma is, gamma II, or.
No, I understand.
Yes. Sorry, I wasn't clear, but so yeah, I wanted to make a qualitative remark here. So what I'm saying here is that the sort of new thing is that there can be II BPS particles But GMW formalism, the main thing is you want to sort of take into account how these II-VPS particles affect the formalism. GMW only know how to do IJ VPS particles, where I is not equal to J. Okay, so in particular, there can be closed solitons. So in other words, if you're solving the flow equation, oops, there's no W anymore. What we have is now alpha. Then you can ask that it go to a 0 at minus infinity and the same 0 at plus infinity. So that would be what an II-VPS particle is. Just a closed gradient trajectory.
Can there be like with no point I just really?
Well, if there is such a thing, then usually there's other sort of things, but we only want to consider. So we're trying to solve things on a line, non-compact line, and then that's why you always want to specify some vacuum boundary conditions at infinity. So
this equation is happening over a point in W plane?
there is no W plane, so far at least, because there's no W. There's only an alpha. But there is something like the W plane. So let me talk about that in a second. Okay, so we want to run something like the GMW machine for such models. And the way to first attempt to do that kind of thing would be to apply the same kind of trick you apply in Morse-Novikov theory, which is work on a cyclic cover, or work on a minimal cover such that P star alpha is exact on X twiddle. So this thing is globally W twiddle for some holomorphic superpotential on the covering space. So you have such a thing, and then what you have is now for each 0, you have a set of critical points with gamma action. What's gamma? Gamma is just the first homology modulo the kernel of P, where P just maps gamma to alpha gamma. So this is the deck group of X twiddle. So you have this thing. You have for each X twiddle, you have some. So you have a gamma torsor of critical points for each 0 downstairs. So you can take that to be your vacuum set. And then the critical values, of course, or the vacuum weights would then be zeta inverse W twiddle of P inverse phi I. That would be your set of vacuum weights. And down on this upstairs thing, periodic or closed path just corresponds to a path that's not periodic, but just something that is between 2 points related by a deck transformation. So the fact that you have these II BPS particles just corresponds to ordinary solitons. So you might say, okay, well, I can just work on the cover and run the usual web formalism with this vacuum set and this vacuum weights. But the problem is this is too naive. And this has to do with the fact that these are not in general position anymore. So for example, if there's a cyclic cover, just gamma is Z, then the critical values are just infinitely aligned. So in fact, there's infinite aligned. So the web formalism is too degenerate. So you need to think a little bit more. So you can choose to work on the infinite, this cyclic cover, or this cover with that group gamma, but you will have to deal with a set of vacuum weights where you have this kind of infinite alignment, and the kind of webs you will draw in this case will be highly degenerate, and it'd be hard to do anything reasonable. So that's the kind of problem that we have to get past. So in the remainder of my talk, I'll discuss some simple assumptions where I know how to do this. So I'll start with an example and then state a general theorem at the end. So that's in the remainder of my time, already at the nearly 2-hour mark. Any questions? Well, so in the example of the isometry that, or the fact that let's say you have a B model with the target space having a U1 action. So those things, so you have a U1 action on some target space X, generated by some vector field Vi. This twisted mass deformation corresponds to adding a term like this in the Lagrangian. So it's an actual mass term. Yeah. And secondly, you can also say that it's the mass of an II BPS particle. So remember, I have this ZII being equals M gamma, well, alpha, which is writing as MQ before. So this is the energy of an II BPS particle. So it also has dimensions of mass.
So what happens in all the BMW theory from generic evolution?
That's the thing, it's not defined, it's degenerate. The webs don't make, it's hard to write down, sensible webs. So that's a wall of marginal stability. And at walls of marginal stability, the GMW formalism doesn't work. So okay. So I will tell you how this is resolved in an example and then state a general theorem at the end. So example. Okay. So the free chiral superfluid is just a B model with the target space C, and you consider the U1 isometry. And turn on a twisted mass for that. What this is mirrored to is the Landau-Ginzburg model with target being C star, the punctured complex plane, with holomorphic one form. And this thing has a vacuum at phi equals m and a non-trivial twisted mass. Sorry, a non-trivial. This is the puncture. This is the vacuum, and a non-trivial closed trajectory. Now, how do you produce A infinity categories that you recognize from something applied to the web, from something like the web formalism applied to this model? So that's what I'll talk about next. So this Landau-Ginzburg A model, I want to produce things that are recognizable from, let's say, the mirror context. So I can obviously go to the cyclic cover C with that group gamma being Z, and then I have the critical points. The V is just given by and the vacuum weights. So again, I choose zeta equals minus I for convenience. And so again, so the problem is that you have so now I'm working on the target. The point is now that ZNM is aligned with ZKL, is either parallel or anti-parallel to ZKL. So you have this kind of degenerate situation, and it's hard to draw things like webs. So the solution, the way you deal with this is kind of simple. Well, you want to consider perturbation.
So what's the problem here? The critical points are not along the line, right?
Critical values are all along the line. So this is just a constant, and thank you. Yes. Sorry about that. Yes. K is in. Okay, so yeah. Now, so now when we're working upstairs, on C, the superpotential is just so, and phi, this is your covering map. Y is a coordinate on C. So now I can choose to do a perturbation upstairs here, such that this infinite alignment is now in general position. So the idea is to do a perturb upstairs, perturb on x2, so that critical values or vacuum weights are in general position. And compute soliton spectrum and interior amplitude for perturbed model. And then, so now that things are in general position, I can run web machine. And then I can try to prove that things are independent of perturbation. Yeah. So run web machine with gamma equivariance. Yeah, in a gamma equivariant way. Yeah. Yeah, but that's the infinity is less scary than the infinite alignment. The fact that you have infinitely many factorial, because I have to run the gamma equivariant web formalism.
The web formalism, it was never important that it's flat. It's only important that maybe that you count the web by area or something. Same as with counting homework. It's never important that in exact case or finally on homework, or not exact case, infinitely none of these counted by area.
Yeah. So I
don't understand how you have been able to recover equivariance after you perturb.
So I want to do equivariance in the way that the soliton spaces still have the symmetry. So yeah, let me illustrate. Yeah, before I had this cyclic central charges, so let me choose particular.
I disagree with you. I think you're opening up a hole. It's not even clear that anything in your theory is well defined. Anything whatsoever. I mean, usually, like in coherent trees, you study the bounded derived categories like finite, complex, and here. You will not know that any of these products vary. You will not know that the theory makes any sense whatsoever. I would think, no?
So you're doing some counting, okay? And before you were doing counting where you knew the counting was finite. So you're all kind of finite. Now you have removed the finiteness, but if you're willing to count by like the length of the web or something, but then it's not.
Yeah, maybe you can rescue it somehow, but it's not optimal, right?
No, I mean, like, I think you could create the same objection to the Morse node about it. But your objection would be eaten at the moment you count paths by the length.
Yeah.
Well,
there's a
covariance solves this. There is no problem because the covariance solves.
Yeah. There's a charge. There's a well-defined charge, and everything is finite in a graded charge. So the particular, so I want to choose a particular perturbation. Instead of, before I had something like zi plus 2, zi plus 1 is parallel to zi plus 1 I is parallel to zi I minus 1, etc. So what I want to do now is I want to perturb things so that the phase has this kind of inequality. By inequality, I just mean the phases are in this way. So this kind of situation is deformed to just opening them up a little bit. So yeah, this is zi plus 1 to I plus 1. This is the I plus 1 I. This is the I minus 1, and so on. So for the critical values, let me just draw another picture, equivalent picture. Critical values, if let's say m is m is real and positive.
Don't you have any dimensions that even a tiny perturbational phase is
It's going to have exponentially.
Yeah. So this thing, which is all on a line, I'm just doing this. I'm moving things so that. So doing this kind of thing, and I can bound it. No, but I can bound it. It's not really a.
You move it by like 1/2,
Yeah.
1/4.
Yeah. So this angle could be theta, and this could be yeah. So. And then now I've traded this problem for trading. So I've traded. Now I need to know the soliton spectrum of this perturbed model and the interior amplitude for this perturbed model. But I claim I know it. Remember, in the unperturbed theory, the only gradient trajectory I had was just a single loop that winds around once. But things are a little different for the perturbed theory. Here I'll have R I plus n is isomorphic to C, so it's one-dimensional. You just write down the generator. It's not the polynomial ring, just generated by this particular element. So this is in degree 0. This is isomorphic to C shifted by 1, generated by, again. So what happens? Huh? No, this is not polynomial. This is just one-dimensional vector space, and I'm calling this to be, I'm calling the generator, so it's just C, and C shifted by 1. So this is what it means. It means, once I do the perturbation downstairs, so before I had this picture, but after perturbation, well, even downstairs I have infinitely many critical points. And there is going to be a trajectory that goes like this. There's going to be a trajectory. So you see that once everything collapses, this just reproduces this. Once I take the perturbation to 0, there's going to be some trajectory like this. This is your Ri I plus 2. This is Ri I plus 1. And this is C star. Yeah, this is downstairs. And once this collapses, it corresponds to a glued path. This path glued to itself. But after perturbation, this is actually a fundamental soliton, and so on. So one winding, 2 windings, 3 windings. So that's Ri I plus 3. This kind of thing. So that's your soliton spaces with this pairings, trivial pairings. And finally, I also claim that I know the interior amplitude. So beta will be given by, remember we had to count triangles. So this kind of triangle, I need to count, this kind of triangle, the deformed theory. And so I know beta, well, claim that it is so for each triple, I greater than j greater than k, we have a unique of a generator, basic generator. So you weigh it by plus minus 1. So one example of this thing would be something as follows. So this is phi equals 0 again. So I could have some trajectory like this. And then some trajectory like this. And then some trajectory like this. Hopefully, oops, sorry, yeah, should go the other way. Yeah. And I can fill it up this way with the Witten equation. Did I screw it up, or will this actually work?
So is it since in that theorem, two upstairs and the line a little bit and
Yeah. Upstairs. Yeah, I thought of when I was writing this talk, I realized that upstairs would be a better picture, but then I was too lazy to actually do it. Yeah. So this is a picture downstairs, and there's something that's filled, and this is, for example, this is something where you have I plus 1, I plus 2, I plus 1, and I. But in general, yeah, you can have multiple windings, and then there'll be some triangle. So that specifies the interior amplitudes, final ingredient for webs. So now I'm ready to compute the A infinity. They're only triples. The other ones are there, but they're not rigid. Yeah. Yeah. So I have to. Yeah. I have to do that too. So yeah, gamma equivariance so far just means that Rij. So this is true as a space for n is in Z. So this is respected.
What is your definition? You take this space.
Yeah.
And define this with the gamma.
Yeah. Yeah. So let me. What I have to do is, okay. Let me just. Okay, so let me compute now the boundary. So remember that the boundary A infinity algebra or A infinity category depends on the choice of a half plane. So let me choose for now the left half plane. The gamma equivariance. So I guess I'll discuss it in due course. I'm sorry. Yeah.
So you have not yet defined the space, closed string space. Yeah. So well, the closed string space, I guess,
is okay. Let me discuss let me define the open string space, and then we can talk about the closed string space. Okay.
So this
Yeah.
is beta. You know, you will have also needed to know the other L infinity products, right? I mean, the L infinity products. Huh?
It doesn't define even the elements of the algebra. It defines something upstairs. What is beta upstairs?
Yeah.
After making this cover.
Mm-hmm.
And then, you know, the actual thing is supposed to take some kind of invariance to data action.
Yeah. So I mean, I've written an algebra upstairs, right? Yeah, and I've written an interior amplitude upstairs. Now let me, instead of doing the closed strings.
The L infinity algebra upstairs.
Yeah. So I know the, well, I know the fans, and I know the central charges. I chose a particular perturbation, and with that perturbation, there's a certain allowed set of taut webs. They can be enumerated, but and that will give you the, you know, closed string algebra upstairs.
Upstairs is just something that you can feed into the old machine.
Yeah.
It just feeds it into the old machine.
Yeah.
Okay. I mean, this is a simple Fukaya-Seidel one and actually solved. So we won't be interested in that. We'll be just interested in some formalization.
Yeah. So okay. Yeah. Yeah, choose the left half plane, and then I want to write down R hat spaces. So I will have, by the perturbation I chose, is this one. Of the full plane.
I think you mean the world shape.
Of the board.
No, but this plane.
Okay.
It's not yet attached to anything.
Yeah. So the A infinity category always involves a choice of a half plane embedded in R2. So
before you could plane, there was no W. Before it was half the W plane. There's no W. What?
this is not the W plane. It's just, this is the space time. This is the.
You define the time category and try to set up that word. You have the W plane.
Well, I always choose half of the space-time plane because I'm interested in boundaries. But I mean, the two are in the Fukaya-Seidel category. What you choose is a zeta, and so
this is not that choice.
yeah. Yeah. Okay. So this thing, yeah. So remember the perturbation I chose. So I chose this particular perturbation where I had this kind of thing. Z I plus 2 I plus 1 was phase ordered as an element of the right half plane, I plus 1 I, etc. So the only half plane fan now is going to be given by so this thing is therefore just going to be C with a generator.
This is half the W. Half the W upstairs.
Well, yeah. So in corresponding to W plane, this would just mean I'm choosing something like this is Wi, it's Wi plus K. Yeah. So I have this this space, and then I claim that the only non-trivial web here is given by this thing, where you have any triple I plus K, I plus K plus L, I guess. And so this leads to the multiplication map. And remember, there was a non-trivial interior amplitude. So now you have something like this, something that essentially looks like this. So now you have to impose gamma equivariance. And the way I do that is I consider
Do you also got a differential?
no differential in this case. There's no web that that has a with one boundary vertex for this particular perturbation that I chose. So there's only.
And where is that built in?
Just which example? You do some example in which things are exceptionally stupid, and then later on it'll get done. In this particular example, it happens.
So he's doing a specific example.
Okay,
Yeah.
he's doing this specific example. In this case, he claims it happens to this guy with no.
Yeah. So I'm just saying that there's a multiplication map. So this is not a polynomial ring again. Sorry, this is just a one-dimensional vector space. Just given by this thing. So the way I impose gamma equivariance is I let so let me call this r hat twiddle upstairs. Downstairs there will only be one vacuum, and I define this to be. So I make a choice of the fiber, and just write 0 n greater than or equal to 0. And this inherits algebra structure from this. So this looks like C plus C. So you have one-dimensional vector space, infinitely many, and this particular product is equivalent to saying that this is just a polynomial ring in one variable.
Could say this, or you could say find the X upstairs take fixed.
Yeah, I'm probably not doing this gamma equivariance part in a neat way, but I have this algebra, and when I pass to the theory downstairs, I just have this.
In terms of the general theorem you're about to say,
Yes.
is it a definition or
This is, I guess you could take this to be a definition. So r hat I is always just defined to be r hat 0 n, where I sum over n positive.
What is the definition?
The composition, yeah. So let's say I want to compose r hat 0 n with r hat 0 m. This is identified with r hat n plus m. Sorry, n plus m, and then I can keep the composition here.
At some point, when you prove things, you're going to have to get some proof that you have to construct an action on the spaces of solutions to some equation.
Right. Well, so I'm just going to be assuming that I'm going to be assuming that property holds. The Rij equals Ri plus Nj plus N.
Rij is set,
or okay, you can, there's an isomorphism. There's an isomorphism between those as vector spaces.
that's not really set. And probably what you mean is that there's a single solution to some equation.
Yes. So
it's not enough to say there is an isomorphism vector space. To prove it, you need to prove it.
I think why not?
Because you might compose isomorphism. What do you have to prove? You have to prove
Well, okay, choose an isomorphism, right?
No, you have to prove it. You have to know those isomorphisms are compatible. Isomorphism are identical. One, but the other one is the same as it.
Yeah.
If it's the case, I'm just saying that's what you need to know.
Yeah. That's a fair point. Yes.
Okay.
Yeah. So you have the first kind of thing that you should recognize from webs, but then there's something also interesting.
So the basic nature of your statement is that you go upstairs, you assume that you've been lived that group space of the short words.
Mm-hmm.
And then you take invariance.
Mm-hmm. Yes.
But that's just an assumption. You're not going to prove it's true in some class examples.
I think so. So by the sort, the fact that there's this unperturbed theory, which has a symmetry, and yes, the fact that I'm perturbing away from this theory, which does have this symmetry, will essentially imply that the soliton spaces in the perturbed theory will have.
And you prove that, or you just leave it?
So maybe if I have time at the end, I will say kind of why I think it's true. Maybe I probably won't.
Why do your angles?
Yeah.
I mean, don't they always somehow increase? How do you end up making a triangle?
So
I thought you always wanted to perturb these in one direction.
So yeah, if I choose this perturbation, then I have this kind of triangle. This is dual to the web I drew.
That's how you get it. Okay.
Yeah. Okay, so right half plane. Now let me compute the right half plane algebra. So now there will be, with the same set of central charges, same set of deformed perturbed z's.
And you say that the distribution list is something that makes sense globally, so we will actually reproduce that algebra.
Well, we have.
I'll trust you.
Yeah. So this diagram is the multiplication of
I know, but
x to the n.
choose a perturbation to show that there is such a perturbation that's going to give you. Of course, we know the answer, so we better get it.
Yeah.
You claim that it's possible to do it.
Yeah. So for the right half plane, now let me choose. So yeah, here I will have, the non-trivial thing to compute is this. And now I will have a whole bunch of fans that contribute. So, for example, if n is 1, then it's nothing special. Then you just have this thing. N is 2, then I have this thing, but also this thing, which I assumed was in this order. If n is 3, I plus 3, I plus 2, I plus 3, I plus 1, I, and then I plus 3, I plus 2, I plus 1, So you have, this, so r hat, in general, r hat, I plus n, I, seems like we'll have a lot of summons. Well, in general, yeah, I mean, in general, it's easy to enumerate what kind of thing you have. It's just given by, you just choose some things that are in between, in the middle. Etc. So, yeah.
So why do you have to freedom to choose like the left half plane or right half plane? Like you take universal cover of the cylinder.
I think right now he's showing that he's checking inconsistencies. Which on the way he's proving to you that inside the left half plane or the right half plane, there's the same answer.
Then not the choice is corresponds to star.
No.
Okay. Yeah, sure, yeah. But that's already fixed. Because you fixed it already.
Yes, but there's supposed to be the same answer, right? Like non-equilibrium.
But just like in the old story,
it's the same answer.
Here, you know, like C, one of your duality, so no, it's not W.
This half plane is on the W.
So in the W plane here, like, well, a fan looks like this for this thing. For the other case, I'm considering.
No, I don't think we're arguing with your calculation. The next question basically like, why would you ever consider both the left half plane and then the next time the right half plane? That's the next question, right?
Okay. So you have this kind of thing. So this would be just one-dimensional in degree 1. This would be one-dimensional in degree 1, one-dimensional in degree 2, and so on. But now, so the claim is that there's a half-plane web. So that looks like this. So for example, here, well, let's look at the one here. Yeah, so here, something like this, or I could do something like this. And then there's an appropriate beta that I can insert here. So let me just look at this one. So what is r hat? I plus 2i. It's going to be C1, C2. And now there's this web. So this summand is generated by phi I plus 2i. This summand is generated by phi I plus 2 I plus 1, phi I plus 1 I. And this web is mapping the different. So there's a differential. So the cohomology of Ri plus 2i is trivial. And in general, you can in fact show that r hat I plus k I is an acyclic complex, where this is the kind of differential that you have for k bigger than or equal to 2. And in fact, okay, what is this? What is this thing actually? R hat tilde. Sorry, yeah, R hat tilde. So.
But before, the corresponding thing, I plus k is always non-trivial, and you're saying this one is always trivial. K these two.
Yeah. The cohomology. That's where I'm going. Yes. So in fact, so this right half plane algebra, which I again take to be So I take this to be R at twiddle I plus, well, n0 as a multiplication and a differential. So the multiplication is given by this kind of picture, and the differential is given by this picture. Is exactly the Kovar complex of C of x. So on the nose. So this is the the Kovar complex of C of x, by definition, is given by so you have variables. So this thing has x squared, x cubed, x to the fourth, and you take a generator for each of these things: alpha 1, alpha 2, alpha 3, alpha 4. And then you take tensor products of them, and then you take, etc. And you consider the differential to be Q of alpha equals alpha tensor alpha, essentially. And so on. And so this is exactly the Kovar complex is, so if you take the cohomology of this, you find the exterior algebra in theta. In other words, the Web formalism, the pictures in this particular case, the Web pictures, are exactly reproducing for you this Kovar differential. And so in this particular example, it works out. And I won't, I guess, go into.
So in this polynomial algebra, was the polynomial algebra graded?
X had, so remember that there was this grading by the gamma?
Yes or no? It's graded or not graded?
X?
Up in the left.
Yeah, so the grading is by just the difference. So you have Ri plus Ni, so it is graded.
So it's non-trivially graded polynomial.
Yeah, well, X has a grading. Yeah. So is that?
That grade is not zero.
Okay, so it's a bigraded algebra where the cohomological degree is 0 and the equivariant degree is 1. So that, yeah, hopefully that answers. And in this case, yeah. So that was just this example, but what can we say about more general things?
I think it's very nice.
So
I think if the C example works, then it's kind of work all.
yes, so in general, what do we expect? So suppose alpha has a single 0 and deck group is Z.
I do have a question though. You make it sound like there is the left symbol and the right symbol. There are definitely examples where they're like, okay, the upward and downward gradient will one pair, but there's more than one side symbol.
So you're talking about
Existence of, I don't know, tiltings and simples and the Verma.
Are you asking about multiple vacua? If there are more than
No. Multiple different sets of symbols.
So yeah, in general, if there is alpha has a single 0 and a deck group Z, and I choose this particular perturbation that I like, then so the A left, which I define as just which coincides with. So there will be some, so in general, there will be some collection of soliton spaces satisfying this equivariance property. I plus. Yeah, well, okay, so yeah, by hypothesis, this equivariance property, and yeah.
Are you picking a vacuum, or does something come before, or is it the beginning of the how do you set a vacuum?
So I'm only, so this is my perturbed.
I know, but
yeah.
Can the covariant charge go negative, or it's always?
Yeah. So the only thing is, yeah, that condition that I wrote before. So anyway, and so then there will be some interior amplitude, beta, which looks like this. Generally it would have, so this would be the trivalent part. This would be the so I have, so I'm just assuming I have this thing with.
Do you have some holomorphic space, and then alpha is the differential on it? What is the beginning?
So the beginning is, well, okay. Let me just take the perspective that I have. I'm equipped this particular set of. So okay, I start with a closed one form with a single zero. That can be closed form, one form on some target X. And it has a single zero, and it can be made exact by passing to a Z cover. Now in general, I will just have this critical values, and then I make this perturbation. After this perturbation, I'm saying I have a collection of spaces Rij with this equivariance property, and an interior amplitude with this trivalent component, this quartic component, this quintic component. So that would be given by counting this and counting this.
In the situation alpha is single zero, is Rij always one-dimensional?
No.
It could be. How does Rij depend on the source?
Rij can be anything. Depends on alpha. So Rij, yeah.
Rij was like the moduli solution to the Witten equation?
To the flow equation, to the gradient flow equation.
What, I mean, don't you, if you have more than one I and J, you want alpha more than?
Yeah, but.
Alpha is doubly, right? So you want to have more than one critical point, right?
Sorry, so R, I plus n. This is what I mean. I and J are both integers.
Okay.
Yeah. Yeah. Yeah, I use bad notation because I used the same thing for vacuum and same thing for indices, and the same thing for the imaginary unit. So it's bad practice. But okay, so the left plane is just going to be, the fan configuration is such that everything just coincides, R0n. And this has an A infinity structure coming from beta, where you have this kind of picture. This kind of picture is the only kind of web that I had that defines, M4, for example. And so, and then the theorem is automatically with no AR, which is on the nose, the Kovar complex of AL. And that follows from the fact that you have, well, the differential, so the multiplication is again just given by this kind of picture, and the differential is just given by, so in the Kovar complex, you have So, and this is the cobar. This is the tensor product multiplication.
What is the definition of AR? Oh, this is the definition. AR is the direct sum of the corresponding things.
Yeah. And this is the cobar differential. So it's so the final result is this kind of Koszul duality statement between the left and the right half plane algebras. So from the webs, we've given a web kind of interpretation to the cobar complex of an A infinity algebra. So I really appreciate your patience. Thank you for your time. Okay. Yes.
I might have missed it, but like, did you have any statements like what algebra is like unlike vector space is like a homotopical?
Yeah. So in fact, that also is very transparent. So if I glue a left plane with a right, if I glue a left half plane with a right half plane, I'll kind of be led to the general Hochschild complex. So the Hochschild complex of an algebra A as a vector space is given by the tensor algebra of, roughly speaking, the dual with